Welcome back. This lecture covers Chapter 12 of Naked Statistics, Common Regression Mistakes. In the last module, we learned how powerful regression analysis can be. This chapter serves as a sort of warning label, and we're going to cover the most common ways that the power of regressions get misused, and sometimes with real consequences. So in the 1990s, the medical establishment embraced hormone replacement therapy for menopausal women. And this was based partially on the Nurses' Health Study, which was a massive observational study of over 122,000 women. It found that women taking estrogen had one-third as many heart attacks as women who weren't. And by 2001, 15 million women were taking it. Then came the gold standard test, a randomized clinical trial where researchers actually assigned some women to estrogen and others to a placebo. When they did this, the results reversed completely. They found that estrogen actually increased the risk of heart disease, stroke, and breast cancer, all these bad things that it was trying to prevent. The New York Times estimated the death toll from this reversal was in the tens of thousands. Regression analysis is powerful, but used carelessly, or inappropriately, it can be dangerous. And in this lecture, we'll cover 7 ways that we can use it inappropriately or carelessly. The first mistake is using regression on a relationship that isn't actually linear. So imagine plotting golf lessons per month against golf score. So for the first $100 or so, more lessons may sharply lower your score. You see a negative slope. And then at a certain point, say between $200 and $300, lessons stop making a difference. The slope flattens to about 0. Then beyond that, more lessons are associated with worse scores. The slope turns positive. There is a real pattern here. You could see it in the scatter plot we have on the slide, but it's not one straight line and one single relationship. It's 3 different relationships that are stitched together. So if you fed this data into a regression model anyway, the software will still hand you a single tidy coefficient trying to represent those 3 different relationships. And the coefficient won't really describe any of those 3 relationships. It'll just be wrong. The second mistake is mistaking correlation for causation. Suppose you're studying rising autism diagnoses in the US over the last 20 years. If you added per capita income in China as an explanatory variable, you'd almost certainly find a strong statistically significant relationship. Basically, because both numbers have been increasing for the past 2 decades. That's it. It doesn't mean that a Chinese recession would lower US autism rates. There really shouldn't be any relationship, theoretically, between the two. They're 2 unrelated trends that happen to be moving together over time. This is called spurious correlation, and it's a reminder that a strong, statistically significant coefficient by itself is not proof that one thing is causing another. Mistake 3 is reverse causality. A relationship between A and B doesn't tell you which one is the cause. So let's go back to golf lessons. If lessons are associated with worse scores, it's probably not that the instructor is terrible and actually making the golf students worse. It's that bad golf causes people to take more lessons. It's not the other way around. The same ambiguity shows up in serious policy questions. So, for instance, states that spend more on K-12 education tend to have stronger economic growth. But does education spending cause growth, or does a strong economy simply give states more money to spend on schools? Often the answer is both at once tangled together. Mistake 4 is omitted variable bias. So imagine the headline, golfers more prone to heart disease. Now this is probably true, but it's probably getting things backwards. So golf, despite the, kind of a renaissance we're seeing of a lot of younger people playing today, it's disproportionately still played by older people, and especially retirees who have the time to spend 4 hours on a golf course. If a regression model doesn't control for age, if we totally ignore that possibility, the golf variable ends up quietly absorbing the effect of age instead. The same trap shows up with school spending and test scores. Wealthier, better educated families tend to live in districts that spend more and have kids who test better. So if we leave parental education out of the model, and the school spending looks like a bigger driver of test scores than it really is. An omitted variable doesn't just kind of weaken your results. it can have really disastrous effects on your estimates. It can even flip your conclusion entirely from a positive relationship to a negative relationship. So mistake 5, this is multicollinearity. Multicollinearity is including two variables as explanatory variables that are highly correlated with each other. So for the example here, suppose you're studying how cocaine and heroin use each affects SAT scores. The problem here with this, and you see by the Venn diagram here, is that almost everyone who's used one of the drugs has also used the other drug. So if you have 692 people who have used both, but only 2 or 3 who've used just one, there's barely any data left to separate the individual effects. And regression needs variation to work with. So when two variables move together almost perfectly, like these two do here, the model can't reliably tell you which one of them is actually driving the outcome. So mistake 6 is extrapolating beyond your data. A regression model is only trustworthy for cases that are similar to the ones that it was built on. So recall the weight prediction model from the last module. We built this entirely on adults. If you plugged in a newborn into that, 21 inches long, 0 years old, the model would predict a weight of negative 19.6 pounds. The actual baby weighed 8.5 pounds. It wasn't that the model was broken. It was simply never designed to answer that question. It was only designed to look at adults. Well, the farther you stray from the range of your original data, the less your predictions mean anything at all. Mistake 7 is data mining. In this case, it's testing so many variables that something is bound to look significant, even if it's just by chance. So here's a classroom demonstration. 40 students flip coins, and each round, all of the tails are eliminated until one student has flipped heads 5 times in a row. The odds of that occurring are about 1 in 32, so it's below our usual 5% significance threshold. But in this case, it's pure luck. It's not skill. Now imagine you can't watch it happen. You just see the coefficient in the spreadsheet. Cram 20 unrelated variables into a regression equation, and on average, one of them will clear the significance bar really for no reason at all. So there are 2 lessons that sit underneath every mistake we covered today. First, designing a good regression equation, deciding what variables are appropriate and belong in it, and what's missing. This matters far more than the actual arithmetic itself. Second, regression only ever builds a circumstantial case. An association is a fingerprint at the crime scene. It's not a conviction. You need theory behind it, and ideally it needs to be replicated with either other data or other researchers trying to answer the same question independently. As the chapter puts it, even a miracle elixir won't work if it's not taken as direct. And we're going to pair this up with the open intro, section 8.2. We'll dig into regression even more and look at the mechanics of fitting that line correctly.